Hello, this is Lazarus at Telecom Tech, where telecom and networking technologies are simply explained. Today we'll be simply explaining the configuration of VPNv4 routes on the MPLS backbone network using Cisco iOS routers. Now, MPLS can become quite complex, and for this reason, this whole video series starts from scratch. If you haven't already done so, check out the first videos in this series, allowing you to gain the required understanding of the fundamentals in order to more readily appreciate the information shared in this video. And remember to subscribe, enable notifications, and like this video if you like this video. And if you have questions or feedback, please write them in the comments below. I'm always happy to read them and to respond. The topology that we'll be looking at today is this one here. For this video, we're going to focus only on the MPLS backbone infrastructure itself. We're going to leave the PE-CE interaction and relationship for the next video. Let me explain a few things about what we're going to do. Although in a production network you would obviously configure all of these routers, for our purposes, we'll only be configuring these 4 routers here, which are the routers that are going to be involved in the exchange of routes and the label switching for the networks of these 2 customer sites. First, we'll be looking at configuring the underlay network of the PE and P routers by creating loopback interfaces and assigning them IP addresses for the purpose of forming LDP adjacencies. We'll also assign an IP addressing scheme to the physical interfaces as well. Next, we'll employ OSPF between all PE and P routers, including the loopbacks, except for those interfaces facing the customers, such as these ones here. Third, we'll enable MPLS on all the appropriate interfaces on the P and PE routers. Fourth, we'll create the appropriate VRFs, RDs, and RTs in the PE routers. And finally, we'll create the IBGP peerings between PE1 and PE2 using multi-protocol BGP, so that the VPNv4 routes will be advertised between them. Let's get started. Here is our underlay network topology and the information with our desired IP addressing scheme. Let's see what our configuration steps are for the PE1 router here. Based on these IP addresses and interfaces, we start by creating the loopback 0 interface and assign it the 1.1.1.1/32 address. We then assign the appropriate IP address to the Gigabit Ethernet 02 interface, which is the interface that faces into the MPLS network and connects to this P router here. We then configure our Gigabit Ethernet 01 interface, which is the interface that faces the customer CE router. And finally, we configure OSPF such that the loopback address, as well as the network connected to the Gigabit Ethernet 02 interface, are being advertised. We don't advertise the network connected to the CE router, however. Now here we've configured this Gigabit Ethernet 01 interface as passive. This isn't actually obligatory, but it is best practice so that OSPF will not send out hello messages to the CE router in an attempt to create an adjacency. Next, let's see what configurations we're going to have on this P router here. As you can see, they're similar to the PE1 router. First, we configure the loopback, then the IP addresses of the Gigabit Ethernet interfaces. Then we configure OSPF and make sure that we advertise the networks of all interfaces, including the loopback interface. Remember, OSPF must advertise the loopbacks between the PE and P routers in order for them to establish LDP adjacencies. Now, the configurations for the underlay of the P2 and PE2 routers are very similar, but we'll show them quickly here for completeness. You can see the Gigabit Ethernet interfaces are configured with IP addresses, as is the loopback interface, and all of those are advertised using OSPF. And the PE2 router here has its loopback and physical interfaces configured with IP addresses and has its core network facing interface and its loopback interface advertised by OSPF, but not its customer facing interface. And once again, as best practice, we have set this interface as passive. So now we've set up our IP addressing scheme, our loopbacks, and our OSPF IGP underlay routing. Now the next step is to enable MPLS and the LDP protocol. To do that, we simply have to enable MPLS on all those interfaces through which the P and PE routers will create LDP adjacencies. That means all non-customer connecting interfaces on the PEs and all physical interfaces of the P routers. Here you can see that we have enabled MPLS using the MPLS IP command on the gigabit 02 interface of PE1 and also on the gigabit Ethernet 02 and 03 interfaces of the P1 router. The same is done on the P2 and the PE2 routers like so. Now we have set up the underlay network, the IP addressing, and MPLS, allowing the P and PE routers to create LDP adjacencies. Now we go on to create our VRFs in our PEs. Remember, VRFs are used to identify specific customers and are applied only to PEs. Let's see what we will configure in our PE1 router. First, we create our VRF, and let's call it green. When you issue the IP VRF green command, you can see that we enter into the VRF configuration mode, and it's indicated by the config-VRF indicator here. Now it's here that we configure the route distinguisher for this VRF, and it is the RD that will create our unique VPNv4 route. Using our context-sensitive help, we issue the RD ? command, and we can see the options that are available for us. We can add our VPN route distinguisher using either the format of ASN:NN or IP address:NN. Remember, the RD is a 64-bit value, so the number before the colon is a 32-bit number, and the number after the colon is another 32-bit number. So you are given the option of using the dotted decimal format of an IP address, which is a 32-bit value, or the value of the ASN that you're using in your BGP configuration. Now note that these are just suggested formats to make our lives easier. You can use any values you like, but it may be useful to associate the RD value somehow with an ASN or an IP address for easier management. In any case, I will be using the 100:1 value since we're going to be using ASN 100 in our MPLS infrastructure when we configure BGP. Now at the same time, under the VRF configuration mode, we also configure our route target, and we configure it like so. Now this doesn't have to be the same value as the RD, but I'll keep it the same just for uniformity. Remember, the RT is used to import and export VPNv4 routes to and from MP-BGP. You can use different RTs for importing and exporting, but I will use the same for both. So now we have configured our VRF and our associated RTs and RDs. Next, we have to associate the customer's interface with this VRF. We do so by going into the configuration mode of our gigabit 01 interface, which is the customer-facing interface on our PE, and we assign our VRF there like so. Now when we do this, we get a syslog message telling us that the IP address we had originally configured on the interface has been removed. This is normal behavior when you assign a VRF to an interface that already has an IP address. So we have to configure it again. And that's it for PE1. Let's quickly see the corresponding configuration on PE2. Now the RDs can be, but don't have to be the same on the PEs since they are used to uniquely identify the networks on the locally connected CE. Conversely, the RTs should be the same on both ends so that they are exported to the appropriate customer VRF when advertised. To keep things tidy, it is always best practice to keep them the same so you can easily identify to which customer they belong. Now finally, we come to the configuration of our multi-protocol BGP, where we will configure an iBGP peering between the PE routers so they can share the VPNv4 routes. We start off with the iBGP peerings. Let's take a look at the configuration in PE1. We do so with our normal BGP configuration using the local AS of 100 and the IBGP neighbor of 4.4.4.4, which is PE2. We also set the source of our IBGP updates to the local loopback interface. Now this is where multi-protocol BGP comes in. Here we configure our BGP peering to share VPNv4 routes using the address family VPNv4, and we activate PE2 as our neighbor for sharing these routes. Now this will automatically enable another feature of BGP. Take a look at the resulting configuration of BGP in PE1. We see that the PE router automatically added the Send Community Extended feature. This is necessary because our RTs are shared using extended BGP communities. Now to complete our configuration, let's take a look at the counterpart configuration on our PE2 router. Here we see the IBGP peering with PE1 is configured, and we also enable the VPNv4 address family so that IBGP is able to share those VPNv4 routes, which are composed of the IP address of the destination prepended with that RD value, making the VPNv4 routes unique on the MPLS infrastructure. So at this point, we have completed our configuration of the ISP network for VPNv4 routes using MPLS on Cisco iOS routers. In the next video, we'll continue this configuration with the setup of the customer devices. We'll also go through several verification steps to see how this whole setup operates in action. So stay tuned for the next video. I hope you found this video useful, and if you have, please click that thumbs up button. If you have any questions, feel free to leave a comment below and subscribe to get updates to newly published videos. I'm Lazarus at Telecom Tech. I hope this has been helpful for you, and I'd like to thank you for watching.